Hello, what I have for you right now is a problem called surfing at work. Now, the idea is that you are acting like a small business owner who has just read in a national level magazine that employees tend to spend 3.5 hours per week surfing on the internet while at work on work computers. This seemed kind of high to you, so you go, wait, that doesn't seem good because I'm paying them for 3.5 hours of work that I'm not getting because they're, playing Fortnite or buying something on eBay or, whatever. So you're thinking, gee, that doesn't seem right, and you decide to study your employees. Now, let's say you take 36 employees and you find an average from that 36 of 4.1 hours per week. Now, this is something of a surprise to you because you thought you were getting work from your workers, and apparently you're not by more than 10%. All right, so I am going to assume that the standard deviation in your company is exactly the same as nationwide. And that standard deviation, again, population, you'll notice that that is a Greek letter, so it's population, is 1.2. All right, so I'm going to assume that. Well, all right, so your first guess is, wow, really, you say to yourself, really, are my workers really spending 4.1 hours a week using company time and company resources to surf the internet? Well, let's use the central limit theorem to find that probability out, or in other words, I want to find the probability that the surfing here, or my x bar, 36, is greater than or equal to 4.1 if the truth really is that national level of 3.5. You go, okay, because we want to see how close we are to what we think is the national level. Well, all right, so we want to do this. Notice I'm looking for the probability of an average. The way I write this is, of course, this is a sample average, so it's x with a bar on top. And my subscript here is n. I recommend you do that just because it reminds you that there is a sample size. All right, so that's what I'm looking for. My central limit theorem says that this probability will convert to z at 4.1 minus what we think the truth is of 3.5 over the true standard deviation of 1.2 over the square root of 36. Notice that is a nice clean square root, and of course that's why you picked a sample size that was so strange instead of 35 or 40, because that gives you a nice clean square root. Hey, when you can take a shortcut, you do it. All right, so you calculate that out, you find the probability that z is greater than 3. Well, now we got a problem because that probability is essentially 0. It's roughly 0.0014 or less than a tenth, around a tenth of a percent. So those odds aren't real good. So you're beginning to think that, yeah, your employees probably need either a little more supervision or firing because you're way above the national average. Okay, so what do we want to do with that? How about the following? How about we actually test to see whether this sample of 4.1 could support a 3.5 truth. Or in other words, I want to do hypothesis testing where I am going to say, gosh, is the true mean? Notice that that is a Greek letter, and the Greek letter means that I'm assuming this is population or truth of 3.5 hours per week versus my alternative of the mean not being 3.5. And I already know that this is a normally distributed problem because I have an x bar. Again, this is business, so what I'm going to do is I'm going to use the same critical value from 95% confidence of the 1.96. All right, so how do I do this test? Well, to do that, I need to create a test statistic. My test statistic, sometimes referred to as T, but be gentle with that because if you keep throwing letters like T around, it's easy to get confused. So I just tend to write it as test statistic because then it becomes clear when you're looking at your work exactly what you just calculated. So there's my test statistic. And my test statistic is going to be the 4.1 minus my null of 3.5 over my standard deviation of 1.2, which I'm assuming again is population and known, over the square root of n, which is 36. So my test statistic here, again, turns out to be 3. Notice the calculation is the same as finding this probability over here. So here's my test statistic. So what do I do with a test statistic? Well, what I do is I set up what's called acceptance and rejection region. If I am using a critical value based on 95% confidence, that means I need 95% in here, which means that each of these tails has to be 0.025 or 2.5%. They have to be because this area sums to 1. So looking up from the tail to find critical value, which again you probably already have learned at this point is 1.96 and minus 1.96. If our test statistic falls in the middle, we have what we call an acceptance region, and that means that we accept the null hypothesis might be true. If, however, our test statistic falls in these outside tails, we reject. I thought I had turned that off. Shush. Now it's off. This falls in the acceptance region or the rejection region. In this case, I have a test statistic of 3. Well, clearly that's way to the right of the 1.96, so I am going to reject the null hypothesis. Well, that's all well and good. Great, I reject the null hypothesis. But what exactly does that mean? Because it's not like you're going to walk into the owner's office, because you're the manager or being the owner. What do the words reject null mean to you? And of course the answer is nothing. So how do you interpret this? That is everything when it comes to hypothesis testing. You reject the null by going up here and thinking about this. I am rejecting this null hypothesis that the mean is 3.5. So I'm going to say the mean is not 3.5. So where is the mean? Well, the mean, if it's not 3.5, means that it's closer to my sample of 4.1. So the conclusion is that your people surf more than 3.5 hours. Indeed, they surf probably closer to 4.1 hours per week. Now you're faced with a business decision of, okay, how do I get my people back to the national average? But that's the business decision based on this set of statistics. So we're finished surfing at work. Thank you.